Okay. See if this works. Sound might not be as good as usual, but try to project to that. Okay, I'm here. Questions?
Could you go over the differences in mass spec between VLBR and nitrogen? Like just what they look like?
Yeah, so you're entirely looking at so here, basically for mass spec in my class, I'm not much of a mass spec guy. This is one place where who you have will really have an impact. Like a couple of the professors love mass spec, know a lot about it. I'm much more into NMR. I don't think any of us pay a lot of attention to IR anymore. And anyway, so what I want you to know about the mass spec is basically focusing on the molecular ion. All the fragmentation that happens after that, we might come back to it at the end of the class, but those are chemical reactions, right? You knock an electron out of the molecule, and then the molecule falls apart. So that is a chemical reaction. Figuring out how chemical reactions work is it's the rest of Orgo 1, it's all of Orgo 2. Like I think doing mass spec before reactions makes that really hard to understand. So you're going to focus on the molecular ion, right? If we look at this, so 35 and 15. So the M plus here is 50. All right, the important thing to remember about a mass spec is you're looking at only like a molecule at a time. So like chlorine has an atomic weight of 35 and a half because 3/4 of the chlorine is 35 and 1/4 is 37. So if you take a big sample, and almost everything else we do, you take a big sample. NMR, IR, pouring it in and weighing it. So it makes sense then to use 35 and a half as the atomic weight. But if I look at one molecule, that chlorine's either going to be 35 or 37. Okay, so we get an M plus at 50, and then we get an M plus 2 plus at 52. Right, so 12 plus 3 is 15, plus 35 is 50. 12 plus 3 is 15, plus 37 is 52. And the ratio here is going to be 3 to 1. For BR, the same thing applies. We say bromine has an atomic weight of 80, but there's really not any bromine 80. There's 50% bromine 79, 50% bromine 81. And so this is 15 plus 79 is going to be 94. And then the M plus 2 is 96. And this is going to be 1 to 1. Really close to 1 to 1. All right, so really the molecular ion here is going to look like a doublet. The molecular ion for and so this would be like 94, 95, and 96. And there'll be like a little peak there for the M plus 1 that you get from, so we got 1 carbon. So 1% of the molecules will have a C13. So the M plus 1 peak will be 1% of that M plus, and then you'd have also a 1% at 97, which is a C13 with a bromine 81. And then nitrogen comes in here, so we get 15. Nitrogen, because it has 3 bonds, kind of throws things off. We get 15 plus 14 is 29 plus 2, so the M plus is 31. And there's not really an isotope pattern with that other than the M plus 1. But it's called the nitrogen rule, and it means that it's an odd numbered molecular weight. for a small molecule, if the molecular weight's odd, there's a really good chance that there's a nitrogen in it. It isn't like 100% proof there's nitrogen in it. And the other place where the nitrogen rule falls apart is there's two nitrogens in it, right? We're back to even. So, like, if you see an even molecular weight, you can't say it doesn't have nitrogen. It could have two nitrogens. And then CH3 is just 15 and 15, so this is 30. All right. And again, you're going to get so there's 30, and then you get a little N+1 peak for the C13. So like I said, each of those peaks represents like a specific molecule with a specific set of isotopes. And so like on small molecules, the N+1, the N+2 are usually pretty small. You can tell, right, so there's bromine for chlorine, right, so we'd have 50 and 52, little peak there, a smaller peak there. Right, you get a 3 to 1 M to N+2. That's chlorine, 1 to 1 is bromine, odd numbers nitrogen. If you're So you guys might do this. Some of you in this room I've talked to who are interested in biochemistry, the BMB major. Like mass spec is a very powerful tool for studying biomolecules. It takes, the reason we've always been able to do mass spec on biomolecules. What's helped now is how much computational power we have, right? If I have 1,000 carbon atoms, very few molecules are gonna have no C13 in them, right? Most of the molecules are gonna have 10 or so. And so there's a bunch of nitrogen, and there's usually some halogen hanging around, like it could be a chloride salt. So anyway, you don't get a peak. You don't get like a molecular ion peak. You get, you know, hair that spans over 50 molecular weight, and the computer can figure out, can interpret that and figure out what the molecular formula should be. For small molecules, we tend not to do that kind of high resolution stuff. We just look at the isotope pattern. So that's basically what I want you guys to be able to do. I want you to be able to pick out if it's got chlorine or bromine or nitrogen. Make sense? All right. There's no microphone. Other questions?
So there was one problem where was like you had like there's like a partial symbol and there's like specific values that should get allocated to. What's up this? Could you go over like or you have to be able to like identify like each one and like
Sure. Yeah. You want me to?
yeah, please go over.
Where was this?
I don't remember if you just didn't have
So I gave you the molecule,
yeah.
and then did you have the table?
We had the values, but then we had to like identify like the next three columns.
Okay. But I mean, you had the spectrum. Okay. Sorry. multiplets are, again, just as a reminder, multiplets are usually, they're signals that have splitting, so they have neighbors, but they overlap. So you can't immediately see what the splitting is. Give you a second on that, and then I'll go over it. Hang on. So in making these assignments, you want to use chemical shift, right? Everything has to fit the proton. If I'm going to say that this thing at 6.8 is L, then the chemical shift has to fit, the splitting has to fit, the integration has to fit. I mean, so there's a lot of information there to take in, right? But this is kind of classic scientific method. If there's a piece of data that doesn't fit, something's wrong. And it might be like the more that fits, like if you have 9 pieces of data that fit and one that doesn't, right? That doesn't mean you blow up your whole hypothesis or theory, right? You tweak it. If you have 2 right and 8 wrong, like you blow up everything. So as you make these assignments, always remember, look at the chemical shift, look at the integration, look at the splitting. Use all 3 of those. If you just try to use 1 or 2, you can screw things up. So I started at the most downfield and I worked my way upfield. You need to know that, right? I put it up in class. It's sort of a OHs down at on the left, downfield, aldehyde, aromatic. So aromatics are going to be, we talked about this some in class today, right? A benzene is kind of a special, it's not an alkene. Those are not 3 alkenes. That is 1 benzene unit. The protons there are going to be sort of 6.5 to 8. It's going to overlap a little bit with a proton on an alkene, which can be sort of 5 to 7. So, and then you get protons on sp3 carbons bonded to electronegative atoms, 3 to 5. I've heard a lot of people say that. You have that down. This one's kind of special. These 2 protons are on a carbon bonded to 2 electronegative atoms, right? So it's an additive effect. If the atom is moving signals downfield, 2 atoms are going to move it farther downfield than your thing. Okay, so let's start up here. 6.8, we got a multiplet that integrates for 2. 6.8 and 6.6, and then 5.9 are probably going to, but that's 5 protons. 5.2. So if we look here, we just sort of draw a line here, right? Chemical shift-wise, we go from 5.2 to 2.6. That's a big jump. And so these 5, 2, 1, 2, sorry, 6. I count like an organic chemist. Okay, so 6 protons here are going to be the 3 aromatic protons, the alkene proton, and the 2 here. Right? Those are going to be the most downfield protons. Everything else is on an sp3 carbon bonded to an sp3 carbon. So you got to work out sort of what's there. 6.6, 6.8, a good bet. Those 3 are going to be on the aromatic ring. But again, that's chemical shift. Check the splitting. Singlet, HD is not going to be a singlet. It's got 2 neighbors. Right? HG and F might be a singlet, but it would integrate for 2. So if you work through that, 6.8 is going to be B and C. A is going to be 6.6, a singlet for 1. Chemical shift puts it on an aromatic ring. So this is HA. And then HB and C It's a multiplet, they each should be a doublet, right? B and C should each be a doublet. C has one neighbor, 1, 2, 3 sigma bonds gets us to B. So B and C are neighbors of each other, and they're the only neighbors. So B and C should be doublets. But if the two doublets come on top of one another, all right, so here's, all right, there's B, doublet. But then there's C. And when those come together, they just add up in a way that makes it really hard to see. There are more sophisticated experiments you can do outside the scope of this class where you can see that those two are coupled to each other and only coupled to each other. So B and C are going to be multiplets. There are 2 of them, so they integrate for 2. A, there's only one A in that signal. It's got no neighbors, so it's a singlet, integrates for 1. All right, then like I said, that's going to leave, I'm going to cross these off as we, so now you don't have to consider those again. Sorry. Yeah.
The B and C, are they magnetically equivalent since they give the same signal?
No, so they're, yeah, it's a good question, and one that comes up a lot. Magnetic equivalence means they are give exactly the same signal, right? And so then it wouldn't be a multiplet. Like they're not exactly the same. 6.8, really one's probably 6.84 and the other one's 6.82, right? So they're offset just enough that they jumble each other up. If they were exactly equivalent, they would be just a doublet, right? So yeah, there's an infinite variety of protons, and the frequency axis is basically 0 to 12. So you're going to get stuff coincidentally in there. All right, so now we've got G and F and D left, okay? So if we look at this, G and F should integrate for 2, and they have no neighbors. So it should be a singlet for 2. We got a singlet for 2. D integrates for 1. There's just one of them. It's got 2 neighbors, I and J. All right, so these here are not neighbors. 1, 2, 3 gets you to the carbon. All right, so D has 2 neighbors. It should be a triplet for 1. So even if, as I did when I looked this molecule up to show it to you, if you just asked me to predict chemical shift, I'd have said D would have been downfield of these 2. But that's not consistent with these 2. So if you just use chemical shift there, you probably get it wrong. But if you look at the splitting and the integration, it becomes clear which one has to be, right? The singlet for 2 at 5.9 is going to be G and F. And the triplet for 1 at 5.2 is going to be D. Questions up to there? Let me ask you. Let me put a different question in right now. What is the relationship between Hg and Hf? They're magnetically equivalent, but then so you've got 2 types of magnetically equivalent. You've got homotopic, the same. You've got enantiotopic. They're enantiotopic. So because they give one signal, they're magnetically equivalent, right? So it's a clean singlet. So if they just were coincidentally in the same place, it'd probably be a multiplet, or it might even look like a doublet if they were both singlets. I've had that happen. I'm going to complain to you about my hard life. I've had that happen where 2 singlets show up really close together, and they look like a doublet, and you spin your wheels thinking you've got a doublet when you've got 2 singlets. But this is just one sharp singlet, so they're magnetically equivalent. They're enantiotopic though if you like replace F with something, right? This group would be R or S. If you replace G with that same thing, it would be the reverse. General rule, actually, I'll go ahead and take your question.
Oh, well, I was just gonna say, which HG, is the HG on the far left, or is it?
Do I have two?
Oh,
God.
The one on the far left is HE.
This is E? All right, good, sorry. And that's not healing either. All right, E and F. HG and F, what's the relationship between HG and F? The new improved HG. This proton and that proton, what's their relationship?
Heterotopic.
They're heterotopic, they're different. So heterotopic means different, and if you look at it and you're like, wow, those are really different places in the molecule, they're just different. All right, so G is on an sp3 carbon bonded to carbons, F is on an sp3 carbon bonded to oxygens. That's different. Okay, so different signals. Where were we? So E and F are enantiotopic. As a general rule of thumb, if a molecule, if the two protons are two groups, it's not just protons, as we'll see in a minute. If the two groups are on the same carbon and they're not in a ring, they're not in a symmetric ring, sorry, or there's no chiral center, they're going to be enantiotopic. Okay, so this ring is symmetric and flat, right? There's nothing coming off the O's, there's nothing else coming off here, so E sort of looks across at a flat benzene ring, F looks across at a flat benzene ring. There's no chiral centers anywhere. If you put a chiral center in the molecule, pretty much every CH2 at that point, those two protons become diastereotopic. Okay? So E and F are enantiotopic. Good, I'm going to stop there. So as we shift down now, let me mark off what we've done. So we've got E and F. We've got D. So now we have G, H, I, J, L, K. So 2.6 is a triplet for 2. 2.3 is a quartet for 2. That's going to be these. So 2's is going to be kind of protons on an sp3 carbon. The sp3 carbon is bonded to an sp2 carbon. That fits both G and H and I and J. And there is no way for you to predict, based on the structure, which one is which. All right, 2.6, 2.3 could be either of those. Right? But there is a way to figure it out. So which one is 2.6? Got to vote for GH, and what did you use to determine that?
Neighbors.
Yeah. So one's a triplet, one's a quartet. So if these were both triplets, like say it was a really long chain, you'd have really no chance of figuring it out. All right. So if there wasn't a D here, right? If that was a methyl, could be either one. If you guys run into a problem like that, either on old test, Wiley Plus, exam on Thursday, right? If there's not data that lets you differentiate them, it's fine not to. You shouldn't differentiate them, right? If the data doesn't tell you which one's which, you just don't know. So here, though, because the signal at 2.6 is a triplet, G and H only have I and J as neighbors. I and J have D also as a neighbor, right? I and J are G and H neighbors and D neighbors. So there are 3 neighbors for I and J, 3 neighbors is a quartet. So 2.6 triplet is G, H. The quartet at 2.3 is I and J. And so that's almost all of them. We've got 2 singlets, 1.8, 1.6. 2 singlets that integrate for 3. All right, so process of elimination, those have to be the 2 methyl groups. What has to be true if those are the 2 methyl groups? What has to be true about the 2 methyl groups? It's an oddly worded question. Are the 2 methyl groups magnetically equivalent? right? If you get two signals for them, they are not equivalent. They're on the same carbon though, so why aren't they equivalent? And the reason is they're diastereotopic. So if you, let's just look at this one. I'll just, that's, right, so if we just look at this molecule, it's got an HX and an HY. HX is cis to the CH2OH, HY is trans to it. If we replace that, if we do our replacement, we get a trans double bond, we get a cis double bond. Cis-trans isomers are diastereomers, so on the blue molecules on the right, HX and HY are diastereotopic. Right, but again, all these relationships, there's nothing magic about protons. This applies to every atom. Okay, so in the example up here, the methyl L is diastereotopic to methyl K. And the reason for this is the double bond is rigid. There's no rotation there, right? If that bond freely rotated, the two methyls would experience the same, on average, the same environment. But because the double bond's rigid, they're held in different electronic states, right? This methyl sort of looks across here always at a CH2. This methyl always looks across at an H. So the electronic environment of those two methyls is different. That means the magnetic environment's different as they split. And like I said, you wouldn't necessarily have to work that out. Like if you get all this, which I'm not saying is easy, but if you do get all this, this works out. Even if you thought going into this, oh, that should be a singlet for 6. When you see 2 singlets for 3, the assignment makes sense. And here, you don't know. There's no way for you to predict, is 1.8 L or is it K? So these are both L and K. And if you were to, okay, tell me how many carbon signals are in this molecule. Yeah.
I have a question. So for the double bond, are you saying that if it weren't a double bond, then those two signals would be magnetically equivalent?
If the double bond were a single bond, right? If we hydrogenate this molecule,
Then they would.
right? Yeah. So now that's going to be a CH2. That's going to be a CH. But since there are 2 methyls on that carbon, it's not chiral. The 2 methyls are anechotopic. They'd be magnetically equivalent.
Sorry, I kind of spaced off there. Could you explain the multiplet one, the 6.8 chemical show?
Yeah. So this is the multiplet up here,
Yeah.
and it's just, I guess you can't see that now, but if you see it while I'm doing it, it might make sense. But just so. HB is going to be a doublet, right? Right, so that's B. C then is also a doublet. But like that's not how the spectrum gets recorded. It just gets recorded frequency. And what you get is you get kind of a weird double humped peak here and a weird double humped peak here. And if you've seen a lot of spectra, you might look at it and say, oh, that's 2 doublets on top of each other. Like that, we certainly do that. We report it as a multiplet. That it's a multiplet simply means they're splitting. Right? So a multiplet, it can't be a singlet. You know those things have neighbors. But they're also not magnetically equivalent, so they don't exactly line up. And really that's what, so I and J, like they're magnetically equivalent. The reason they integrate for 2 is there's really a signal for both of them that just reinforces completely, so it makes the signal big. All right, number of carbons. I'll give you another little bit. And I should probably count myself. carbons? How many unsaturations are there? All right, if you've had if you're watching this and you've had your volume turned up, turn it down. Okay, how many carbon-13 signals are there? Got to vote for 10. More? Sorry? You shouldn't bid against yourself. No. Okay. All right. Anybody want to go over 11? Okay, so there are. Did I count Did I count how many carbons there are? Right. That's always 6, 7, 8, 9, 10, 11, 12, 13. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, and there's 2 O's. 2 O's I was pretty sure of. Okay, so which? Sorry. What's your vote? If you say 11, which carbons are identical? Which carbons are magnetically equivalent? Okay, so that's, yeah. These are not equivalent. So 13's right. There's actually not any magnetically equivalent carbons in this molecule. Right? So these are really similar, right? So these 2 carbons are benzene carbons bonded to an O, bonded to an aromatic CH. And if that's as far as you go, they're the same. But if you keep going, the aromatic carbon with an H, they're bonded to, this one's bonded to an aromatic with an H. This one's bonded to an aromatic with a C. All right, so they're not equivalent. You can also do the replacement test. Yep. B and C are, no, they're not. They're homotopic. They're just, right? They're. B and C, right? All right, so there's our molecule. If I replace HB, I get that. If I replace HC, I get this. All right, so those are 2 different molecules. If I take this molecule and lay it here, they don't overlap. They don't overlay. So that means B and C are just, they are non-equivalent. So there might have been some confusion here. Just because they overlap and make a multiplet does not make them magnetically equivalent. All right? Non-equivalent atoms can overlap coincidentally. I'm trying to think of a really good friend of mine in high school shared my birthday. This is a terrible analogy. If this hurts, if this doesn't help you understand, just put it out of your mind. She and I shared a birthday. Are we equivalent? She was 5'2". I'm not 5'2". I don't believe she weighed 100 pounds. Once upon a time, I didn't weigh 100 pounds. I think I was 7 or something. Right? So we were not equivalent. We just happened to have the same birthday. There's only 365 days in the year, so you're going to overlap birthdays. People are going to overlap birthdays without being twins necessarily. And so the 2 protons in this signal just coincidentally have a frequency that's close to the same. It's not exactly the same. It's close to the same. So they're magnetically non-equivalent. They're heterotopic. They're different. But they're coincidentally in the same place. Okay, so basically there's no symmetry in this molecule, right? None at all. So every proton, I mean, there's enantiotopic protons that are magnetically equivalent. But none of the carbons are equivalent. Yep. Uh-huh.
You'd be able to tell that, right?
Right. So if I asked you to sketch that, I mean, you could be a smart ass and be like, yeah, all the aromatic protons are a multiplet for 3 and all the others are lined up, you know. If I asked you to sketch it, I'd want you to tell me, right, that HB is somewhere between, and you don't have to say it's at 6.8. You need to tell me a region it's in, right? So it's like 6.5 to 8, something like that. And you tell me it's a doublet, and you tell me it integrates for 1. And then you'd say HC is a doublet in the same region, integrates for 1. So if you're making assignments, multiplets are a little hard to deal with. Okay. So 13 carbons, how many unsaturations? 5, or are you raising your hand? Okay. Got to vote for 6. Do I hear 7? All right, so unsaturations are pi bonds and rings. Pi bonds, 1, 2, 3, 4. Rings, 1, 2. So 6. And you could get that. This is a terrible time to tell you about this. Right? There's this formula, so it'd be 2 times 13 plus 2 divided by 16. So this is 26. Sorry, not divided by 16. God. Minus 16 divided by 2. So 26, 28 minus 16, 12 divided by 2 is 6. All right. Don't use that formula unless you don't have a structure in front of you. So that might come in handy on your unknown. I don't know if, do you get, on the lab unknowns, anybody looked at the lab unknowns yet? Is there a molecular formula in those? Or is it just a mass spec? Yeah. I sometimes, if the molecule I choose, so on the final project, there'll be one of these, probably on the final exam, there'll be one of these, where you have to take all the different spectra and put them together. If the mass spec doesn't really clearly tell you something, I sometimes will give you a molecular formula. The molecular formula can tell you how many unsaturations there are, right? And if you have more than 4, there's a decent chance you have a benzene ring. So a benzene is always 4, 3 double bonds and a ring. Did that address your? Good. The same reason as the protons, right? So they're diastereotopic. This methyl is cis to an H. This methyl is cis to a CH2. So the H's are not magnetically equivalent. The HL and HK are not magnetically equivalent. That means the C's are not going to be magnetically equivalent. Right? That whole thing about relationships, I kind of focus on protons, but it applies to every atom. Like you can have enantiotopic phosphoruses. You can have diastereotopic nitrogens. It's about the magnetic environment, not about like the identity of the element. Yeah.
So, like, for the carbon signals, like, what are we, like, would the whole molecule have to be chiral for us to, like, have less than, like, the same number?
No, actually, chiral molecules tend to be less symmetric. So you'd need, a lot of times the benzene can work out, like, and even if there's something chiral and really wonky, like, all right, let's do this. So I'm pushing a bit here, I think. I think you can do it if you take your time and a deep breath, but there's some weirdness to this one. Anybody got a vote? We have a vote for 11. We have a vote for 12. First of all, so this is a trivial one. I actually meant to say this when I wrote the molecular formula. So there's 1, 6 is 7, 8, 9, 10, 11, 12, 13. There are 14 carbons in this molecule. Your answer really should not be above 14. I see that sometimes. Like make sure, like that is a theoretical limit on the C13 signals. Okay, so this kind of goes to this idea of chiral centers. The alkyl group over here between the oxygens, there's a chiral center, and that's going to throw some things off. A chiral center reduces symmetry. But the benzene ring is actually symmetric. There's a plane of symmetry that goes right here. And you might say a very reasonable thing to say would be, well, wait a minute, right? That H, you might say that HA and HB are in different environments. That HB sees this whole alkyl group and HA doesn't. But what's going on here, remember, this is a CO sigma, this is a sigma bond. So there's free rotation around that bond. So that whole alkyl group, on average, swings around a few hundred million times a second. And again, this is one where you haven't run an NMR, but if you think about the physical thing we're doing with an NMR, we pulse the molecule, we put it in a magnetic field, we pulse it with a radio wave, we excite all the protons, or carbons, sorry, in this case, and then we listen to the carbons relax, right? That actually takes several seconds for all the carbons to relax. In the time that carbon relaxes, that alkyl group swings around the CO bond, billions of times. And so what matters is the average environment A and B are in. All right? So A and B are actually in the same average environment. And so that means those two carbons are the same, are homotopic, they're magnetically equivalent. And these two carbons are magnetically equivalent. All right, so we're going to get, hard to see there, there's now a methyl group. All right, so the methyl carbon is 1, that carbon is 2, 3, 4, and 5. Carbon 5 and carbon 2 are not the same. Carbon 5 is bonded to an O, carbon 2 is bonded to a C. O is not a carbon. 6, 7, 8, 9. I think everybody's in agreement up to here, right? So now and then let's just do this. We'll skip. We'll say that's CH2 bonded to an OH. There's not another CH2 bonded to an OH in the molecule. So carbon 10 is by itself. So now the 11 versus 12 debate is, what is the relationship of these two carbons? Got protons on the brain. Those two methyl groups, what is their relationship? If you haven't thought about it yet, think about it for a couple of minutes, or a minute. Is that a hand up or just, yeah. I'm a big believer in, I think you need to move to think. Not you personally, but just people. So same deal goes, I told you on exam 1, if you need to stand up to do a chiral center, if you got to wave your hands around to figure out how many carbons or how many neighbors there are, that's fine. So what's the relationship of those two methyls? You got to vote for enantiotopic? Another vote for enantiotopic? So if they're enantiotopic, 11 is the right answer. Got to vote for a diastereotopic. Is it weird that I like to run this like an auction? All right, so if I replace the wedged methyl with X, that X is on the same side in this conformation as the methyl. That methyl's opposite. So in that environment, again, it matters what the average is. So that's why enantiotopic protons or enantiotopic atoms are magnetically equivalent. On average, they end up being in the same environment. Here, they're going to be diastereotopic. Okay, so I'm going to go through this in a little. I'm going to separate out. Those two methyls are diastereotopic, and the answer is 12. I want to go through that a little bit because I think there's still some confusion as to when something's enantiotopic and something is diastereotopic. So let's see. All right, so X and Y here are going to be enantiotopic. And again, like I said, two protons on one carbon are going to have a hard time being homotopic. Because one's in front, one's in back. That's going to be tough to always be exactly the same. So if we replace, we get that, and if we do the back one, we get that. Those are enantiomers of each other. Right? So the two HX and HY. What this test tells us, remember, these molecules don't really exist. This is a thought experiment. The fact that we get enantiomers out of our thought experiment tells us that HX and HY are enantiotopic. That means they're magnetically equivalent. There'll be one signal for them. All right, let me do one change. My knowledge of the alphabet's being tested. All right, I've only made one change. I've added one methyl group. But that makes a chiral center. Okay, so this right there is chiral. Now in our thought experiment, when I replace HW, you don't change anything else. So all right, that methyl stays front. That's replacing HW. If I replace HV, again, the methyl group stays front. So the fact that there's a chiral center there tells us that the CH2s, the two protons in that CH2, are going to be diastereotopic. Okay? So, right, if you look at these two molecules, one chiral center stays the same, one chiral center changes. And now, what that really means, like functionally, that's a cool test and everything, and you can learn to do it. But what it means is, even as this molecule tumbles around, and remember, it's going to go through hundreds of conformations in the second it takes to record the spectrum. So you're looking at the average place where this proton is. But what it tells you is, right, HW is looking across here at a methyl, HV is looking across at an H. They're in different environments, and it's not going to average out just by spinning around. All right, so the long and the short of it is, if there's a chiral center in a molecule, CH2s on it, like an sp3 CH2 is going to be diastereotopic. Same thing is true of a ring. If you have if you have a chair, right? That's not a chiral molecule. Methyl cyclohexane is not a chiral molecule, but if we look at the H's here, hope I'm not giving anybody flashbacks with a chair. Right? One of those H's is, so that's down and the methyl's up. So this H is trans to a methyl, this H is cis to a methyl. And that's going to stay the same if you do a chair flip. So those two protons now are diastereotopic. If I replace one, I get a cis isomer. If I replace the other, I get a trans isomer. So rings and chiral centers, like non-benzene ring. Benzene rings are flat, a lot simpler to deal with. But a ring that has some shape to it, or a chiral center is going to pretty much turn any two groups on the same carbon into diastereotopic atoms rather than enantiotopic. So a chiral center, and that's kind of what I heard sort of a, well, chiral make it, a chiral center or a chiral molecule tends to make spectra much more complicated. Tends, I mean, not always. Did that help? Because I think, okay. Like enantiotopic and diastereotopic could like I think most people have down like those are the same and these are different. Enantiotopic, diastereotopic's a tough test. Juliet, and then, what's that?
I forgot what I was going to say.
Okay.
Can you go over on like the last worksheet why the molecule is more stable than like the positive charges on the C versus the positive charges on the N and the other?
Vice versa. Yeah. Yeah, so that one was, well, I can do all these. Let me, I know you didn't ask for this, but. All right, from there, so secondary carbon, secondary carbocation. You can move the charge here. And this is actually, there's a lot of stuff going on here. Nope. There's actually two reasons, only one of which is really obvious for you guys. Right, the cation on the right that I drew is tertiary. So tertiary cation is more stable than a secondary cation. The other is now you regain this benzene ring, and like I've said, and at this point I'm just asking you guys to take my word for it. A benzene ring has this special quantum mechanical stability. Benzenes are really stable. The other one was, I think, and the one you were asking about, all right, so this one, and I think a fair number of people sort of just said there's not a more stable resonance structure. Okay. Like, that could be true. In this case, though, the nitrogen lone pair can form a pi bond. And so I think the question is, and I've had this from a few people, right? Now you get a positive nitrogen. And this is more stable. And rightly, so is your question about why the more electronegative atom being positive is more stable? It's a good question. The reason is the octet. So the carbon, this carbon only has 6 electrons. So a carbocation, sort of by definition, doesn't have a full octet. And I don't think I probably in chapter 1 and 2 didn't bang this drum enough that not having a full octet, being positive, having a positive charge, that is, there's a lot of different ways to have a positive charge. You can have a formal positive charge, H3O+. But in H3O+, even though the oxygen, by bookkeeping, has the positive charge, that positive charge resides out on the hydrogens. Right? So like if a base reacts with H3O+, it grabs a hydrogen. It doesn't grab the oxygen. When an atom has a positive charge because it doesn't have a full octet, that atom itself really has that positive charge. Like that is a strongly positive, I mean, I don't know how many different ways I can say it. Not having a full octet is a very destabilizing thing. It's less destabilizing for carbon than nitrogen or oxygen. I think we went over that in class a little bit today, if you saw that video, if you were here. An oxygen that lacks a full octet essentially doesn't happen. Okay, that is so unstable. It will have a positive charge. It won't have enough electrons. It's really unstable. So here, yeah, the more electronegative has the formal charge, the formal positive in this structure. But again, the charge is that anytime you have a formal charge, it's distributed over the molecule. This carbon is really bearing most of the positive charge, the partial positive, because the CN bond is polarized. So this structure is more stable because all the atoms have full octets. Here, the carbon does not have a full octet. Okay, so the other one was sort of related. Right, so that's your structure. And now there's two different ways to go. You can move the electrons down from the oxygen or you can move electrons in from the nitrogen. And both nitrogens can do this. And so if you do that, here's the structure you get. Both the red and the blue structure are more stable than the black original structure for the same reason, right? The blue and the red structures, all the atoms have full octets. In the black structure, the carbon doesn't have a full octet. But now, between these, right, the blue one is more stable. And that is for the electronegativity. So now having the positive nitrogen, having the positive on the less electronegative element, nitrogen instead of oxygen, is more stable. So if all the atoms have full octets, you can use electronegativity. And most of the time, well, with anions, where you use ARIO the most, like anions, everybody's going to have full octet. You got an abundance of electrons. So the atoms are going to have full octets. In cations, where you might not have a full octet, that rule takes priority over electronegativity. More?
Can we do like some ARIO practice? Yeah, basis.
So I have to invent a problem. It's past my bedtime, so I'll try. ARIO. All right, so one equivalent's just a word. Basically, we have the same number of moles of these two molecules. Remember, I can't make this point enough, you never have one molecule. So if we have like 1 millimole of the molecule on the left, we have 1 millimole of the molecule on the right. Once you've done the black one, we'll talk about the black one first, but then we can talk about the bottom one. Shouldn't do that on camera. okay, on the top one, which molecule is the base? Yeah, so again, base is an electron donor. So the more dense the electrons are on something, so you often, not always, but often the negative charge is going to be the base. So right, like we've got lone pairs kind of all over the place here. So we got 2 lone pairs on this nitrogen, got a lone pair on that NH2. Neutral nitrogens are very often bases. Neutral nitrogens are reasonably strong bases. And then, of course, we got 2 lone pairs on this oxygen. Neutral oxygens are weak bases. Like water is a weak base. Alcohols are weak bases. The rule is, anytime you look at one of these, strong acids are going to react with strong bases. So you want to identify the most basic atom. You got an N minus. So the other thing on ARIO, like in terms of the basic atom, that's not really I guess, is it ARIO? Anyway. If the basic atom is the same, like nitrogen, nitrogen, carbon, carbon, oxygen, oxygen, the more negative that atom is, the stronger the base will be, right? So a negative nitrogen is a stronger base than a neutral nitrogen. Hydroxide is more basic than water. O minus is more basic than neutral O. Okay, so you answer the question right, you still get a lecture. So that's the base. Now, that doesn't mean the other one's got to be an acid. It's a review session. You know, we're less than 48 hours ahead of the exam, so you guys are thinking he's not going to put a reaction up that just doesn't do anything for sure. And you're right. This reaction is going to do something. But just because you have a base doesn't mean you automatically have an acid. The other thing is this would always have to have a cation with it. Right? You don't have bottles of anions or cations floating around. So there would probably be a lithium plus with this. We can go upstairs right now and I can find you bottles of that salt. Right? If you keep it away from acids, it's stable. It's fine. If it sees a little bit of water, sees a little bit of alcohol, it's gone. All right. So this is the base. So the question you need to ask, is this an acid at all? Like it's got to be an acid of some sort to get an acid-base reaction. It is, right? Again, neutral alcohols, OHs are weak acids. Actually, an NH proton can be pulled off if you have a strong enough base. The CHs probably aren't going to react. The Cs aren't going to react over here. So which proton on the right is the most acidic? This is kind of ARIO too.
It would be the one on the O because it's conduction.
Yeah. So ARIO, atom is first. The proton on the more electronegative element is going to be the more acidic one. So if we're trying to decide between an OH, an NH, and a CH, the OH, and especially if you look at that, right, the negative charge you get by pulling the H off is going to be localized on all these. If I pull the OH proton off, I get a localized O minus. If I pull an NH off, I get a localized N minus. If I pull the CH off, I get a localized C minus. OH is going to be the more acidic. So this is going to be that. And this is where one equivalent comes in. So if there were 2 equivalents of the base, you could imagine it pulling off an NH there. And so now, well, let's do ARIO first of all. Which side's favored? The right is favored, right? So ARIO, negative nitrogen, localized negative charge on N, localized negative charge on O. O is the more electronegative element, so the right side is favored. ARIO works really well. I've talked with a bunch of you in office hours, just hanging around, that ARIO is not like the law of gravity, okay? It fails a fair amount. Where it's most useful is where only one of the 4 applies. Okay, so if the atoms are different and the orbitals are different, maybe it works. If the atoms are different and resonance is there, maybe it works. Right? And something that maybe works, that's not terribly useful, right? We want to rule here. There's no difference in resonance. There's no different in induction. There's no different in orbital. The only difference is the atom. So this slam dunk that the right is favored. Yeah, that's it. That's really, what else was I going to say about this? Seems like there was something else I was going to say about it. But that's, yeah, so the right is favored. All right, do the bottom one. Yeah, sorry.
So on that last one, when you're doing that, you're comparing the base and the conjugate base.
Right, yeah, okay, I think that's where I was going with this. You always have to decide, am I comparing the base and the conjugate base? Am I comparing the acid and the conjugate acid? All right, because you want to compare, I want to compare this structure with that structure. Right? This one either protonated or deprotonated, this one either protonated or deprotonated. I don't want to compare this with that. Right? If I compare the deprotonated version with the protonated, well, clearly this one's more stable. It's neutral. But that, I mean, is there something that can protonate it? So you can you can compare the bases. What I just did with ARIO is I'm comparing the negative here. All right, so this is a localized N minus, localized O minus. Okay, so that's comparing the atom in the base. I'm comparing the base and the conjugate base. You could also compare the pKa's. And you'd have to have some idea of this one. And you could get this off the pKa table that I showed in class. This one's going to be about a neutral alcohol, pKa between 16 and 18. All right? A neutral NH. This is not an NH2+. This is just a neutral NH. pKa here is about 34. All right, so again, if you just have that kind of ballpark learned, like if you thought it was 20 and 30, or you thought it was 12 and 38, like it would be hard to get those numbers. That's a big enough difference, it's going to be hard to swap those numbers. So you can, yeah, you can do ARIO, and you tend to want to do that with the more unstable pair, right? If I compare this neutral molecule, everybody's got a full octet, everybody's formally neutral, it's stable. Again, I could put this in a bottle and keep it. This amine, same thing. It's neutral. Everybody's got a full octet. It's hard to get much of it. How do you look at those and say, well, this one's more stable than that one? That's a really hard thing to do. I'm not saying the other one's easy, but now you've got some instability, right? N minus, O minus, there's something reactive about those. So compare those. Use the ARIO to compare those. Yeah.
So for the pKa, are you using the OH functional group?
Yeah.
pKa 17?
Yeah. The point is the pKa of the acidic proton. I tend to say, I think everybody tends to say this. That molecule has a pKa of. It's really that proton has a pKa of. All right, so a molecule can have multiple acidic protons. So this proton has a pKa of 17. That has a pKa of 35. All right, a couple of minutes on the blue. See it? Okay, so which one's the base? One of the negative charge. The base does not have to be on the left. I probably draw it that way more often. A larger point I've tried to make
reactions are always driven by electrons. So bases really are driving the chemistry, right? That's where the curved arrow starts. I didn't draw a mechanism up top, right? So this mechanism is going to be from the N minus to the H, the OH electrons onto the O. So I tend to think of base first, then acid. So I think when I'm just drawing these up. Don't do that on the exam. I actually write an exam and then give it some thought and mix and match. So yeah, O minus, you have excess electrons here. You got a carboxylic acid over here and an alcohol. So base, acid. Which proton in the acid is most acidic? OH more than the OH more acidic than the CH, right? So which OH? Right. So carboxylic acid, and now this is R of ARIO, right? If I pull this O off, I get O minus. If I pull that if I pull this H off, I get O minus. I get O minus either way, so A is the same. Right. Induction's actually different here. Orbital's the same, but resonance, this is a localized O minus. You got resonance there. This O minus is delocalized on the two oxygens. So again, pKa here is about 4. pKa here is about 16. Right? So that's a big difference. 12 orders of magnitude is a big difference. A localized negative charge versus a delocalized. So now our mechanism, the O minus is going to take the H, OH electrons onto the O. OH, and then, okay. And the pKa here is also, should say about 4. pKa is about 4, right? This is really like 3 to 5. This is 3 to 5. So unless you have memorized the pKa's of these two carboxylic acids, you can't tell me which side's favored. You're going to have to use ARIO. You could tell me that they're going to be within a couple orders of magnitude. Like equilibrium constant's not likely to be 1 billion here, right? They're going to be fairly close. The other thing you learn by the pKa of this one being in the range of 3 to 5, it is not a strong enough base to pull that proton off. Right? So even if I had a whole bunch of the base on the left, if I had more than one equivalent, it's still not going to pull the alcohol OH proton off. Okay, so which side's favored? Yeah, so A is the same in both cases. R is the same in both cases, okay? O minus delocalized, O minus delocalized. Orbital's the same. But we have an inductive effect. So over here we just have alkyl groups. But on the left, on the right, that CO bond is polarized. The oxygen is electronegative. By induction, it's electron withdrawing. So an oxygen can be a resonance donor, but by induction, it's going to be withdrawing. That CO bond, hang on to that. You learned that like probably in high school chemistry. Right? A CO bond is polar with the carbon being partial positive, the O being partial negative. And the fact that that's sort of pulling electron density this way makes this carbon more positive than it otherwise would be. If that one's more positive than it otherwise would be, it pulls from there a little bit. If that one's more positive, it stabilizes the O minus. Right? Inductive effects are through sigma bond networks. So they're not as strong as resonance. And they decrease pretty quickly over distance. Right? So if we had this, for instance, right? If we move that OH farther away, we reduce its effect. Well, I mean, it's still, even with this OH, that one is still more stable than this one.
Well, no, those two, the bottom one
Yeah.
would be
This would be a stronger base than that one, yeah. That's another thing with acid base to always keep in mind, right? If you want to know how strong a base is, look at its acid, right? If you know that the acid, that its conjugate acid is really strong, you know the base is weak. It's always an inverse relationship. Right? If I have a strong base, its conjugate acid's weak. If I have a weak base, its conjugate acid is strong. If I have a moderate, the other one's moderate. Another, did that help? The exam's not tomorrow, right? I'm just going to give you advice to get some sleep tonight. You should still get some sleep tonight. Sleep is important. Yeah, that look tells me you need some sleep. All right, another quick question, anybody?
On the stereochem for the reactions, I was trying to figure out like how like chiral racemic or achiral will be like it must be racemic. How can an achiral molecule be racemic?
It can't. So that was a chiral molecule that's racemic. Like if you have a reagent that's chiral, but it's racemic. Like if I dump into the reaction racemic starting material, then the product has to end up racemic. Like the only way to get a chiral non-racemic product is if something in the mixture, and it could be the substrate itself, it could be a reagent, it could be a catalyst, technically it could be a solvent. Something has to be chiral and non-racemic to end up with a chiral non-racemic product. You bet. So yeah, that was a chiral racemic or achiral. Either one of those are going to give you a racemic product. All right. I'm done, I think. So send me an email. I believe Mo has a review session or some sort of mock exam tomorrow night. I have some office hours tomorrow, I think. And I'm through about half of the addition homeworks. I will get those. Uh-oh. My phone has a low battery. I'll get those done probably by tomorrow afternoon sometime. So have a good night.